Welcome to episode 5 of the Euler project, a video series in which we use Clojure to solve the problems in the online Euler project and then take them to the max. Euler 5 is one of those nice little problems. In this case, it's about finding the least common multiple of a large bunch of integers. There's nothing particularly difficult about solving this problem. On the other hand, as we follow through with our investigations, it will demonstrate to you that no machine learning, no artificial intelligence will ever replace a programmer. So here's the problem. We're just going to find the smallest number that is the multiple of all the numbers between 1 and 20. That's the least common multiple of that sequence. I suppose we could just look up the algorithm and implement it, but wouldn't it be more fun to use test-driven development to see if we can derive that algorithm? And so we begin here with the most degenerate possible case. The least common multiple of an empty array should equal 1. And of course it's failing right now because the least common multiple is returning nil. And so we will make that pass, of course, by having it return a 1. All right, so now the next test would be something slightly less degenerate, although this one still passes, so okay, fine. The least common multiple of 1 is 1, yes. All right. The next test is still fairly degenerate, but it gets away from the 1. The least common multiple of 2 is 2. This is going to fail, of course. And let's see, how can we make this pass? Well, how about this? Okay, so that's lovely. That one passes. Can't say I like the algorithm much, but okay, we're doing TDD. That's the way that goes. So the next test should fail. Let's see if it does. Yes, it fails. And that's because the least common multiple of 1 and 2 should be 2, but I'm just returning the first. Now, I think I can make this pass by doing something fairly ugly. Whoa, okay. I'm just going to multiply all of them together. Now, I think that's going to work. Yeah, that one works too. Okay, and maybe you're looking at that and thinking that's absurd, but I'm trying to find the least common multiple. Well, as part of that, I ought to first try to just find a multiple, and of course the greatest multiple is just multiplying them all together. Although using apply and star like that might not be the best approach. Let's do it this way. So reduce star, yes, we're going to reduce multiply with the beginning value of 1 and then all the numbers. So that's the same thing. I think that's still going to work. Yes, it does still work. But that's a little bit better than using apply, because you don't know how long that list is going to be. And besides, this is probably more, I don't know, philosophically accurate. Okay, now this is kind of interesting because the if statement over here now, I think the if statement is redundant because if ns is empty, this is just going to return 1. See what I mean? How that apply, was not quite right. So if I get rid of the if statement, I think this is still going to pass. Oh yeah, see, it still does. So that was a very nice simplifying move. It got rid of that apply, it got rid of the ugly if statement. That was actually kind of nice, wasn't it? Okay, so here's the next test, and this test is certainly going to fail. In this case, we are really trying to find the least common multiple, and multiplying them all together does not work. But we've got this interesting algorithm over here. It's just a plain old reduce. And the issue is that I'm multiplying them all together. It seems to me I need to do something a little more intelligent than that. Something like multiply. But that is not quite multiply. Now, what would that be? The problem with multiplication is that it gives us the greatest possible multiple, not the least common multiple. So we need to find some way to replace the multiplication with something that's like multiplication but gives us the least multiple, not the greatest multiple. And in the case of two numbers, well, that's just this. It's the product of the two numbers divided by the greatest common denominator of the two numbers. So let's do this. Let's add an overload to our LCM function that just takes two arguments. And this one is going to do this little formula of ours. We're going to multiply a by b and then divide by the greatest common divisor of a and b. And if it's not two arguments, then we're going to take in the list and treat the list appropriately. And this one, well, the one is okay. I think the star is going to have to be changed, but we'll get to that in a minute. Now, the greatest common denominator of a and b, for the moment, we're going to let that be 1. And the reason for that is that I don't think that changes anything, right? We're still just multiplying a by b and then dividing by 1. So we get the same result down here. So that's a good starting position, right? Our tests fail for the same reason. So now we need to figure out this greatest common denominator function. So let's disable all of our least common multiple tests here and describe what greatest common denominator is. And our first test for greatest common denominator, once again, is this degenerate test where we say, okay, the GCD of mutually prime numbers is 1. And I think that's going to pass already, so let's just see if it does. Yeah, okay, it does. Right. And I've turned off all the other tests, so I'm not going to be complicating things with that. So the next test is if a equals b, well, then the greatest common denominator is just a or b. It doesn't really matter which it is. This should fail, and it does. Good. So, how are we going to make that pass? Okay, I suppose that makes it work. If they're equal, we just return one of them, and otherwise we return a 1. So that makes these tests pass. Not a great algorithm, I get it, but okay. So the next test is where b divides a, 3 divides 6 in this case, and the greatest common denominator is just the smallest of the two. Now this fails, but I think I can make it pass pretty easily because I think what's going on here is that if they divide, then I want to return b, right? So here, let's just change the if statement. If the modulus of a and b is 0, well, then we'll return b. Otherwise, we'll return what should we return? Well, I think that makes it pass. So that works. If they divide, then we return the divisor. Otherwise, we return a 1 because they don't divide. Okay, so here's the next test. And this is the case where they don't divide evenly, but there is a greatest common denominator, which of course is 4 in this case. So 4 divides both 8 and 12. And so our current algorithm will not work. Yeah, okay. So we need to replace this 1 with something. And we need to replace the 1 with something that is like 1, but is not 1. And what do I mean by like 1? Well, it has to be like 1 in that it divides evenly both of the arguments. Yeah, something like that. So what is this thing that is kind of like 1 but is not 1? Well, let me tell you about this guy named Euclid. Euclid of Alexandria, a Greek born 300 BC, the father of geometry. He wrote The Elements, describing the process of geometry, that whole mathematical structure of postulates and theorems and lemmas and things like that. He's often thought of as one of the most influential mathematicians of all time. In the pages of Euclid's spectacular book, he defined the algorithm for finding the greatest common denominator of two integers. And it worked something like this. Imagine a rectangle, and the rectangle has sides which are the two integers. This is going to be a side of 6, that's a side of 15. The length of the sides are the two integers that we want to find the greatest common denominator of. Now, Euclid supposed that the greatest common denominator of 6 and 15 would be the side of a square that completely tiles this rectangle. If we can find the largest square that completely tiles this rectangle, then it will have a side equal to the greatest common denominator of 6 and 15. I will let you stew on that particular insight for a while. But let's follow the algorithm. The algorithm works like this. We first find the largest square that will fit inside this rectangle. And of course, that's going to be a 6 by 6 square. So 1, 2, 3, 4, 5, 6. Okay, that square fits in the rectangle. Well, looks like we could put that square in again. So 1, 2, 3, 4, 5, 6. There it is again. Okay, so we've got a little remainder. If we did not have a remainder, then this would be the largest square that completely tiles the rectangle, and the greatest common denominator would be 6. But that's not the case here, is it? Because there's a little rectangle. And this little rectangle is 3 by 6, isn't it? So, okay, we've got to fill that with a square now, and that square is going to be, well, let's see, it's 3 by 6. That square is going to be like so. Those are two squares, 3 by 3. The greatest common denominator of 6 and 15 must be 3. Now, we've seen something like that before, haven't we? Remember back in episode 2-2 when we were doing that Fibonacci stuff and we drew those square spirals. Remember those square spirals when we were investigating repeated fractions? Let's crank that old program up again. So let's draw the square spiral of sides 27 and 21. Let's see how that looks. There we go. There's our original rectangle. There's the first square. And then, oh, well, it looks like we're going to have 3 there, and oh, 2 more there, and oh, looks like we're done. And over here, you'll see the sides of these squares. So the first square was of side 21. Well, that's kind of obvious because that's the 21 side, right? And then this is the 27 side here. And that means there was a leftover, so, you know, a remainder. And so it drew another one, another square, and that had a side of, you see, 6, right? There was a 6 there. Okay, so we have squares of 6, of course, and then, well, there was a little remaining rectangle there, so we needed to divide that one up into 2, and it divided evenly. And so what's the size of this little square here? Well, the size of that square is 3. So the greatest common divisor of 27 and 21 is 3. Now, does this square tile the entire rectangle? Well, it clearly tiles this side, right? Tiles that side, right? It evenly matches, which means it tiles that square. And that means it tiles that square. It means it tiles that square here. And since it tiles this down here, then it certainly tiles this whole rectangle right here. But if it tiles this rectangle, that means it evenly divides that side. And so it tiles this side here. But this side is equal to this side, so it must tile that side, so it must tile the entire rectangle. Now remember, we started this by asking about some kind of replacement for 1. Something that was like 1, but was not actually 1. Now here is the 27 by 21 rectangle, and I've done all the work here, and you'll notice that the square that tiles this entire rectangle is a 3 by 3. That is the unit of tiling. That square is the tiling unit. And the word unit is equivalent to the word 1. So it's this unit square here, this 3 by 3 square, which is the unit of tiling, which is in some sense the number 1 in our algorithm. Do you see what's happening here? We've seen this twice now. Twice. Both times we started out with test-driven development, and test-driven development led us to the overall structure of an algorithm, but then left us a dilemma to solve. In the least common multiple case, we needed to replace the multiplication operation with something that was kind of like multiplication but wasn't exactly multiplication, and what we came up with in the end was multiplication scaled by the greatest common denominator. In the GCD case, what we've realized is that we want to replace the constant 1 with the notion of the tiling unit. In both cases, test-driven development led us to the overall structure of the algorithm and also made us puzzle about something concrete that seemed like it ought to be more abstract. And so in both cases, we needed to hunt for the underlying abstraction. And that is the secret heart of programming. Programming, when you boil it down to its pure essence, is the hunt for the underlying abstraction. And finding that abstraction is a purely human attribute. No machine, no artificial intelligence, no deep machine learning program has ever been able to find the underlying abstraction. The intuitive leap that realizes that finding the greatest common denominator of two integers is the same as finding the largest square that tiles the rectangle defined by those two integers is something that only humans have ever been able to do. So let's go back to our 21 by 27 square here and notice that the ratio of the two sides, 21 to 27, can be reduced to lowest terms by dividing through by the greatest common denominator, which gives us a ratio of 7 to 9. And of course, those two numbers are mutually prime, and therefore the size of the square that would tile a 7 by 9 rectangle would be the unit square. The true unit square. The true 1 by 1 unit square. Okay, I think I've made my point. That square represents something like the number 1, and it somehow fits into our GCD algorithm right where the number 1 is. So how does it fit in? All right, so I know we keep winding up back here, but look at this one last thing. Here's the unit of tiling right here, that square. And that square completely tiles this larger rectangle here. It has no remainder. But every other attempt did have a remainder. So for example, when we tried to tile by the 6 by 6 square, there was a remainder. And when we tried to tile by the 21 by 21 square, there was a remainder. So this algorithm is about remainders. And so now look, we've already got the remainder in here, and we're already terminating this if the remainder is 0. If the remainder is 0, we return the divisor. So what should we return here? Well, this is that thing that's sort of like 1, but isn't 1. And of course, what that is the last square And the last square is just the GCD of b divided by the remainder. That passed. Fascinating. But we're going to pass the remainder back in here. So it seems to me that that could just be this. And then what should we return? Well, we should return A in that case. Gee, I think that's still going to work. Oh, yeah, that still works. Heavens. Is it really that simple? Yes, it really is that simple. This is Euclid's algorithm for finding the greatest common denominator. But discovering this algorithm required a remarkable insight into the geometry of the problem. And that was one of Euclid's great gifts. He was a master at being able to visualize mathematical truths using geometry. But we've still got some work to do here. We've got to go back and figure out the least common multiple of all of those numbers. So let's uncomment out those commented tests and get back into it. So here are our tests again, and I've uncommented them, and of course they're failing. And our problem was to replace this multiply here with something like multiply, but that is not multiply. And what is that? Well, it's LCM. It's this function here, which is like multiply, since it does multiply the two numbers together, but it also scales that multiplication. And if I do that, oh heavens, now all my tests pass. Look at that. Even the LCM tests pass. Isn't that lovely? And, well, now I believe we have all the code we need to solve this problem, to solve Euler 5. So, the Euler problem gave us an example. They told us already that the LCM of the numbers from 1 to 10 should be 2520. And remember, the range function goes up to, but does not include the final number, and so that's why that's an 11. And I think this is going to pass. And it does. And so let's try the actual problem. Okay, so here we're going to find the least common multiple of the numbers from 1 to 20, and the answer is... Ha-ha! 232792560. Well, let's go see if that is the actual answer. And yes, that is the actual answer. 232792560. That was the answer. So, we have solved Euler number 5. Here, let's just change that nil so that it now passes our test. And now our test should pass. Anyway, what's the takeaway from this? Well, it's happened to me more than once that the first few tests in the TDD cycle will provide for me the outline of the overarching algorithm, but leave behind some kind of abstraction that I'm missing, the underlying abstraction. This happened to us twice in this problem. First, we saw it with the least common multiple, where the abstraction missing was something based on multiplication. It had to be like multiplication, but could not be multiplication. And in the greatest common denominator case, it was the abstraction of the number 1. Anyway, I hope you enjoyed this. I hope you learned a thing or two. And you're not going to want to miss the next exciting episode of the Euler Project, episode 6, Problems Galore.